By now, we've talked about how to handle two categorical variables and how to handle a categorical and continuous variable. What about when we have two continuous variables? When both our variables are continuous, we can use correlation. This is the degree to which two variables show a tendency to vary together. Visually, you might imagine a scatter plot with one variable on each axis. The more linear the association, the stronger the correlation between these variables. With chi-square and the t-test, our real interest was the p-value. In correlation analysis, we still start with the p-value. If it indicates significance, we also need to look at the correlation coefficient. The p-value, as usual, tells us whether or not an association is statistically significant. The correlation coefficient tells us both the strength and direction of that association. Let's start with direction. The relationship can be positive or negative, also called direct or inverse. Positive correlation means that as one variable increases, the other also increases, and as one decreases, the other decreases along with it. Negative correlation means that they move in opposite directions. So as one variable increases, the other decreases, and vice versa. In other words, they move in inverse directions. Association strength comes from the numeric value of the coefficient. Values will always be between -1 and +1. If a value is 0 or very close to 0, it indicates no correlation or very minimal correlation. If a value is 1 or -1, it indicates perfect correlation. In the case of -1, it's perfect inverse correlation. These are rare. Usually you see some number in between. If it's very close to 1, it indicates a strong correlation, very close to 0, a weak correlation, and somewhere in the middle indicates a moderate correlation. Now, there are no hard and fast cutoffs, though generally in the social sciences, a good rule of thumb is that above about 0.65 is a strong correlation, below about 0.3 is a weak correlation, and anything in between we might consider a moderate correlation. But sometimes this may vary depending upon the exact question you're asking and the variables you're working with. If you think back to your algebra class, you can sort of understand this graphically. A positive correlation indicates a positive slope, and a negative correlation indicates a negative slope. The strength of the values is how tightly the data fit around this line. But what the correlation doesn't tell you is what the line actually looks like. What is the slope? To understand that, come back for the video on regression. One thing we have to be very careful about in interpreting correlation is the question of causality. Causality indicates that one variable has a direct and influential impact upon another. And sometimes this may be true, but sometimes it's not true. Remember, correlation does not equal causation. Just because two variables are correlated does not necessarily mean that one causes the other. There must always be a logical, or we might say theoretical, reason to call something causal. And causality is where we get into the differences between dependent variables and independent variables, which we will talk about more in the regression video. As a rule of thumb, in the social world, rarely is one single thing the sole cause of something else. Here are some examples. Does household spending on groceries correlate with household spending on prepared food? There might be some association here. We are talking about two aspects of food spending. And we can turn to the Household Pulse survey again from the census. And we find that there is a statistically significant association, and the correlation coefficient is around 0.53. So it looks like there is a moderate association between these things. But it's also not perfect, and that's probably in part because prepared foods, they're just a little different. They're often a little bit more expensive than groceries. And so this is a category of food spending that's going to relate, but not be exactly the same. This is also a great example of the correlation does not equal causation maxim. We have clearly demonstrated that these two variables are related to one another. But does one cause the other? I mean, it makes sense that they relate, but to say that increased grocery spending causes increased prepared food spending, or to say that increased prepared food spending causes increased grocery spending, I mean, there's just no logic there. A more likely cause of both of these factors would be income. The more money that someone makes, the more they may spend on food. Now, there's probably some limits there, and again, it's probably not the only causal factor, and also, a person can only eat so much food anyway. But now we would have a situation that makes sense to consider causality for. However, in this data set, income is an ordinal variable, meaning we can't use correlation. We would have to use ANOVA and t-tests to explore that further. How about age? Does food spending correlate with a person's age? And the answer, unsurprisingly, is not really. We do have a highly significant p-value. That's probably due to the fact that we have an incredibly large sample size, but the correlation coefficient is only 0.06. That's very close to zero. And this makes sense. There's no real reason that one's age may have an impact on how much you spend on food. And there's definitely no way that how much you spend on food is going to impact your age. The command to run correlations in R is fairly simple, core.test, and we'll talk about how to use it in the analysis assignment and in our class Zoom session for this week. In that assignment, I will also show you how to graph these things. I showed you a scatter plot earlier, and that's not one that we've talked about before, although conceptually it's pretty similar. And in the analysis assignment for this week, I will introduce you to two new functions in the graphing universe that help you do this, geom point and geom smooth.